Okay. Well, first of all, thank you for having us today at this wonderful conference with our kind of off-topic topic, automotive. My name's Chris.
My name is Kevin.
And yeah, let's start. Okay. Before we start, we have a short disclaimer just to tell you that all we're going to say today is our personal opinion and not the one of our employee. And please respect, we're not going to answer questions regarding any products or strategies of our employees. So, yeah. So who are we? We were already introduced. So the only update is Kevin finished his master thesis and is now also a PhD student. And if you want to get in touch with us, you see the contact right here, and just take a picture and get in touch if you like. Okay, so what we're going to talk about today is about a diagnostic protocol for modern vehicles, and we give you a brief introduction of what's changing in the automotive industry, what this protocol looks like, and in the second half, Kevin is talking about how we can use the features of the protocol to do some forensic analysis on state-of-the-art vehicles. So, how is the automotive domain changing? In the center of everything, with a focus on security, I'm pretty sure most of you have heard of autonomous driving. That's kind of a trend over the last couple of years. And what this means is that cars are getting equipped with more and more sensors like radar, LiDAR, ultrasonic wave cameras. You have sensor fusion, so it's getting more complex. We also have mobility services, so you like to connect your mobile device with a car, or the car's connected to your smart home, and you also hook your car up with a charger, and there's communication with the internet, and of course the car themselves have internet connection. So this also leads to more interest of criminals, and that leads to misuse. For example, if you don't want to pay for a service that the company manufacturer offers, you try to get around that and get it for free, for example. So it's a huge interest, and of course car theft is also still an important topic. But what's really interesting and new is there are new legal laws coming up and standards. I'm pretty sure some of you are aware of the ISO 26262. That's regarding safety. And what's new in 2021 and 2022 is the UNECE and the ISO 21434. That's kind of the same thing as the ISO, but for cybersecurity. So as a manufacturer, we have to have certain processes and have to monitor our vehicles and stuff. So if you're interested in that, take a look at the current draft. It's not released yet. So what was the motivation for our research? Myself, like we were introduced, I'm interested in the in-vehicle network security. I like testing and forensic and automotive protocols. Kevin's into malware analysis, forensic, reverse engineering, and also into automotive security. So we thought, well, can we actually do forensic on a state-of-the-art vehicle? And how could we do that with state-of-the-art technology? So that's what we talk today. If you're interested in more details about our work, we have some publications coming up next year. So just keep track on that if you're interested. So as being an ICS conference, we thought it might be a good idea to do some comparison between an automotive vehicle and the ICS. So what they both have in common is the systems run fairly long. Well, it depends on the system, but cars should run like 20 to 30 years. At least we're responsible for them for 30 years. And in both systems, patching is difficult. I'm not an expert in ICS, but what I've heard is certification is a real thing. So if you want to do updates or patching, you have to make sure that you get your certification. And it's kind of the same in the automotive domain. If you change something in a safety function, you need certification and clearance. And what's different in the ICS to automotive, the distribution of updates and patching at the moment is mostly calling back vehicles into the service shop and doing updates, and that's kind of expensive. Regarding operating systems, this is not a complete list, but just to give a short overview, most of the ICS systems are controlled by Windows and Linux systems. In a vehicle, we have up to 10 different operating systems, like real-time operating systems, POSIX-based systems and stuff. So that's pretty complicated at some time. And interconnecting ICS systems to the internet proved to be a bad idea in the past. The goal for common vehicles and upcoming vehicles is all the vehicles should be interconnected with the internet. So let's see how that works out. Both use standardized and proprietary protocols, and it's the same in the vehicle. So let's dive into the protocol. At first, how it all started with public awareness, because automotive security wasn't a huge thing in the past, but it all started really 2013 and 14 with the publication of a Tesla hack. And also Miller and Velasek published a lot about the Jeep hack. I'm pretty sure some of you saw that on the Black Hat conference. And in Germany, it really got off with the BMW hack that was found. And by the ADAC, it's like the Automobile Club, the biggest one in Germany. And since then, a lot of publications came out with different brands and different manufacturers. So now we have public awareness for such topics. So the technical scope of the presentation today is we are hooking up our laptop, which is the analysis device, with the car. What's new? Diagnostics was already a thing over the last couple of years, but now it's Ethernet-based, so you can connect a device via Ethernet, and that's what we do. What is not in scope is we don't look at wireless interfaces like mobile broadband, Bluetooth, near-field communication, or Wi-Fi, and we don't look into ECUs directly. So let's talk about the protocol. So what's DoIP? The name is Diagnostic over Internet Protocol, and it's a transport protocol to transport diagnostic messages into the vehicle. It's specified in the ISO standard 13400, and it's also using the number as a port for UDP and TCP. And it's based on a request and response paradigm. I often get asked, so what would explain DoIP in the easiest way? I would say if you know UPnP, it's kind of a UPnP for cars. So you can shout out, is there a car available? And it will answer, yes, I'm a car, and give you some information. In general, the protocol has 3 different types of devices. For one, the diagnostic equipment. Some of you maybe have seen that in a service shop. You connect it, you have software on that knows what to do. Inside the vehicle, you have 2 different types of devices. It can either be a node or a gateway node, and the gateway node is responsible for transmitting and translating different kind of protocols between the diagnostic equipment and the device. To give you a better overview, on the right-hand side, we have a simple stack representation. So you see it's Ethernet, IP, UDP, and TCP, and then there comes DoIP, and above that is UDS, which I will explain in a second. And then you have the service payload that you send to the device. So what is UDS? UDS is a unified diagnostic service. It's been around for a couple of years, but in the past it was transported by older bus networks like the CAN bus. I'm pretty sure in the OT environment the CAN bus is known because it's often used lately. It's specified in the ISO standard 14229. It's also based on request and response, and the payload that you can send to the device is also defined in different other standards. So you can actually send whatever you want, as long as you defined what you want to send. It's based on an addressing. So to identify a device within the network, you have 2 bytes to address the device. And each device offers, they call it a service. So it's like an RPC call, but you make the call not via a name, it's always by a number. So you have 1 byte that addresses the service that you want to trigger. Again, on the right-hand side, you can see a simple stack representation. And on the left half of it, you can see the CAN bus. It uses ESOTP to do segmentation. And above of that is UDS. So on the right-hand side is DoIP. So both are used to transport the request to the end device. So how do they work together? You connect your diagnostic equipment to the vehicle via the OBD the OBD connector. And in most of the vehicles that we saw, you have like a gateway node that's responsible for translating requests from one bus technology to another. So if you only have CAN bus within the vehicle, it transports the Ethernet requests to CAN and back. And you can imagine it like you have a lookup table with addresses that you have inside the vehicle, and you know which technology it uses to communicate, and then things are getting translated. So what can we do with these diagnostic messages? We can read data, we can write data, we can modify device parameters, which is actually writing, but it's common to say to modify parameters. We can trigger device actions, like do a reboot or do a software update, and we can trigger protected functions. So these protocols offer security features, but as always, it really depends on how the manufacturer implements the standard. So if you use a weak password or one like PIN for every vehicle that you have, that's a really bad idea. So best always use vehicle-specific codes. So protocol composition. The protocol really is kind of dynamic. You have a certain standard that you have to obey to. You have legal authorities, like for exhaust analysis, if the police officer wants to do an analysis of your vehicle, they have to provide and implement certain services. But besides of that, the protocol lets a lot of room for the OEM and the supplier to implement their own services. And what sometimes is really a problem, they implement services to do debugging while the development phase. And it happens that at the end, when you build the final software, things like the debug interface get forgotten and they end up in the product. So that's not really good. And that might be an attack vector. So that's about the protocol. So what have we done in our research? We wanted to do an approach without any proprietary tools that you can buy on the market. So what we did, we analyzed the standard and we implemented both protocols in a Python library. We also built a diagnostic stack in Python to communicate with the vehicle and implement some state machines. And then on top of that, we built a scanning application to read some information out of the vehicle. To implement that, we needed, like we heard it today a lot, we had PCAP files, but the problem is there aren't any dissectors available for these protocols. So what we did, we also implemented a dissector to be able to read and interpret the information that we gathered. So to give you a short example, I hope you can read it. On the right-hand side, on the left-hand side, you can see it's a screenshot from Wireshark without having a dissector, and it's just random bytes. And over here, you can see the protocol, and you can read all the fields. It's human readable, and that helped us a lot while implementing the software. Now the question is, so what's the fuzz all about? Usually, if you do diagnostic with a vehicle, it's a point-to-point connection. So you have a tablet computer with the OEM software on it, and you connect it, and you do your diagnostic. But with being Ethernet, a packet-oriented protocol, you could just hook up your car with the next available Ethernet port, and maybe you have your computer to do the analysis somewhere else. So that's the example down here. And if you have a small network like a service shop, they have their own IT department, and you have your office network also connected to the same network as the vehicle. They are accessible by simple office computers and to the internet. So we have also the usual attack vector, phishing emails, and maybe malware that is specific for vehicles. So we thought we take a look at it. Can we take it further? And sort of question we were asking us was, can we find vehicles in a network that we don't know? So what we did, we implemented an Nmap module, and we were able to identify with network port and IP ranges vehicles in the network. And after that, we thought, okay, can we take that even further? And can we kind of mess around with the diagnostic equipment or the vehicle? And as it turned out, yes, we can. We had some ideas. We're not going into detail about them today, but let's say the smallest message we were able to define that messed with the diagnostic equipment was only 11 bytes of payload required to do so. So there's a lot of room for malware. And what we can do with that protocol is Kevin now explain to you.
Thank you. So how can we use the data we are able to gather? So what we can do, we can perform automotive forensics. We define automotive forensics as the use of digital forensic techniques and methods to gather data or evidence which we can later use. And all this must be stored on the in-vehicle or in the in-vehicle systems itself. We separate the mechanisms, the techniques, and the methods into live and post-mortem forensics. Live is that the vehicle is running, so for example, the car is still driving. Post-mortem is the vehicle is switched off, and we are performing analysis on the device itself, on the devices itself, so on the different components. The acquisition itself is separated into an online or an offline manner, where we have an online manner, so the system is kind of running, so all components are communicating with itself. And in the offline manner, we are soldering, for example, or taking the vehicle apart, taking one component and analyze the one specific component without any interaction with the other components. So in order to perform or use automotive forensics, we most of the time need to present in front of court. For this, we have different requirements we need to fulfill in order to generate sufficient and usable evidence. So first, the tools and methods we are using need to be consistent. This means that everything, every connection we are drawing between people, between systems, need to be logical and comprehensive. Next is the functionality. The methods and techniques we're using need to be functional and proven to work. So every time we are doing this. Robustness is if the environment we are in, so the vehicle, the model, if this changes, there is no need, or we should not need new tools and new implementations in order to perform forensic analysis. Next is acceptance. All the techniques and methods we are using, or technologies, should be accepted by the forensic community. This is why we present a lot our research, write publications. Integrity. The data we need to collect, or we are collecting, and the data we are storing and analyzing need to fulfill the integrity requirements, so this should not be changed during the analysis, beforehand, and afterwards. Reproducibility is if we perform multiple analysis multiple times, we should get similar results, and it should always work. So this brings a lot of research challenges with it within automotive forensics. What we did, we looked at different digital forensic challenges and mapped them onto vehicles to learn from them. So first is the complexity problem. As Christopher already mentioned, vehicle systems get, with each iteration, new model, more and more complex. So we have new mobility services, autonomous driving, connections. So this is relevant for vehicles too. Diversity problem within digital forensics is if we have a big chunk of data, let's say from an SSD or an HDD, and we need to separate this big chunk of data into small chunks in order to analyze it sufficiently. Within vehicles, we don't have this problem because the memory we are acquiring from a specific ECU is kind of small. The consistency and correlation problem is that we collect different sources, data from different sources, so multiple ECUs, for example, and afterwards we need to correlate them in order to perform timelining analysis and build sufficient evidence. The quantity and volume problem is kind of similar to the two above. This means that we collect data from different sources, and at the end, if we finish with data acquisition, we have a lot of data we need to analyze. This is relevant for vehicles because in newspapers and in publications, you always read that we have more than 100 ECUs installed in a modern vehicle, which is a lot. The unified timelining problem or challenge is if we get data from different sources, so for example from different ECUs, time is interpreted differently within these ECUs or within these subsystems. For example, if you have one ECU which is very, very time independent, so it needs time, it needs a very exact time, and other ECUs don't have this requirement, for example, in the beforehand of on the design of the vehicle. And the problem we are facing is that the time can drift away, and as a result, timelining can be very, very difficult. So what we did then is we developed automotive forensics concepts, which needed to be very, very abstract in order to use it on different OEMs, on different models, and to be adaptable. So first we will start with forensic readiness definition, then the data acquisition, the data analysis, and finally, last but not least, the documentation. So forensic analysis is forensic readiness, is basically defined by first defining which data sources are present within a car and which connection interface we can use to acquire or to get this data. Here we're using the OBD2 interface, as Christopher already mentioned, and the data we are collecting at this time is internal flash and external flash memory from different ECUs. Next, we have to check if we have tools to actually acquire the data and later analyze it. Here, as Christopher mentioned too, we have this Python framework, a self-built OBD2 Ethernet cable in order to connect our analysis computer to the vehicle or to the network of multiple vehicles, and Wireshark to analyze the packets afterwards. So for both of those things, it's a checkmark for us, so we can fulfill it. But the last one is kind of difficult. So the last one is the level of development for a specific domain. And our domain is the automotive domain. There aren't that much resources we can get for automotive forensic analysis. Most of the resources are based on the infotainment system or on CAN, and we are looking at automotive Ethernet-based systems. So it's kind of new for us. But we did a lot of pre-analysis on multiple vehicles, multiple systems. As a result, we cannot give it a check mark, not on cross, but kind of equal, so it's okay. So next up is the data acquisition. Since we are in our research, we're kind of acting like an unindependent researcher team, so a third party with no internal documentation. We don't know which systems or ECUs are installed within the car. So what we do is we use the ODS protocol in order to check out which target addresses, so which destinations and which devices are installed within a vehicle, and we are iterating basically over all possible target addresses. Afterwards, we will have a list of different installed devices, and we can use this list to send multiple UDS service identifier messages to those and acquire data. Here are 3 examples. For example, we can determine which repair shop was the last one accessing a device, or which testing device or tester device was used. Also, which was the last installation date for the software or for the hardware of a specific ECU. While communicating with the car and using our analysis computer, we are capturing the traffic, storing it in a PCAP file, duplicating it, creating a hash file of it, or the hash of the PCAP, and storing it on an external device. The copy of the data will be used for the later analysis I'm presenting now. So first, we will only look at positive responses. For UDS, the service identifier is hex 62. For the positive responses, this means that the ECU is actually sending data back to us, to our analysis computer. And if we did this, we can determine which evidence or frames are interesting for us. Some are interesting, some are not interesting. I will show some later. One example here is that we can determine changes to the software. For example, if you have an illegal tuning scenario where an OEM or, for example, someone wants to determine if the vehicle was tuned and the software was modified, you can use the top 2 UDS service identifiers, so has the hardware changed or the software changed. And if you have above this a message where the repair shop identifier was also changed, you know who was the last entity which was connected to the vehicle. So, as already mentioned, some data is usable, others are not. You can see here 2 examples. To your right-hand side, you can see one example which is readable. This is an ODX file data identifier. This is a file which stores different events, diagnostic events, and at the bottom you can see the data record string. This means where do we have to look to collect this file. As Christopher already mentioned, within those protocols, the supplier and the manufacturer can define his own codes. And here we can see one specific code. It's 2A to F in hex. This is vehicle manufacturer specific. We can read the data record string, however, we cannot interpret it. To interpret the data, we either need internal documentation or reversing the whole protocol for this specific model of a specific OEM, and then we can or could use it. So last but not least, the documentation. During our analysis, we document every step. We work in pairs. At the end, we consolidate everything into one final documentation or report. And the report needs to be ready for possible court presentations. Therefore, no inconsistencies should be present within this report. As a result, we perform multiple reviews. Ask questions or stated questions like who was the attacker, who was the lost entity which changed something, who was connected, need to be answered within our report. The goal of the report is first to present it in court, and second, to allow any third party to reproduce the results which we performed. Yep. or God. So during our analysis and during our work, we identified multiple gaps within modern vehicles. So first, we don't have any tamper-proof storage within cars at this moment, which means the data we are collecting is not that trustable, to be honest, because it's kind of easy to change it. We have no standardized EDR, which stands for Event Data Recorder, which stores predefined events. Okay, yeah. Next is that we don't have any forensic tooling or limited forensic tooling, and the tools are usually for one specific OEM or for one specific model. We have very big differences between the different OEMs, and even within the models for specific OEMs, there are very big differences for performing forensic analysis, automotive forensic analysis, and acquiring data. However, we see a lot of opportunities for automotive forensics. So first, we usually use static memory for the microcontrollers. This means, if available, we can look into the memory maps and can acquire data kind of fast because we know where to look at. Next is the memory you're acquiring is kind of limited. As a result, we can perform fast acquisitions. The performance of in-vehicle components is increasing statically with every new version. As a result, we can perform a lot of pre-analysis within the car, and the amount of data sources is very high. Here is our measurement we took, where we have an average bytes per second of nearly 700. This is just us talking with the vehicle. So I mentioned before the gap that we don't have EDRs in European cars yet. EDRs, yeah, in European cars. By 2020 or 2022, sorry, there is a need for event data recorders in Europe. As a result, we have one dedicated storage device where we can collect a lot of data at the beginning, so we can perform an initial triage if the data is usable. Next is that embedded forensics is very well established. In addition, the similarities between general computer systems and vehicles are increasing, so we can learn from both domains a lot and use them in the automotive forensics domain. So in the future, we also will have hypervisor-based controllers, which means that we have one big hypervisor, and we can perform different operations within those different hypervisors if they're separated. So to sum everything up, Christopher presented you the protocols, the modern protocols, which pointed out that connecting vehicles into the company network and a big network is usually not that good and holds a lot of potential security risks. Also, there is no malware for vehicles yet. So this is kind of unknown. We did some stuff, but we never encountered real malware for our vehicle. In addition, which was mentioned by Christopher too, is that we, with the protocols in vehicles, it always depends, or the security level always depends on the implementation the supplier or the OEM developed. So I presented to you automotive forensics, which we are currently looking at, that the forensic readiness shows a lot of gaps, which we need to deal with. However, automotive forensics holds a lot of potential data sources we can acquire. There's a lot of data within cars, and with each new iteration, there will be more and more and more data which we might use. In addition, in the future, we will have, due to the mobility service, a lot of issues or problems or challenges regarding GDPR compliance, because vehicles hold a lot personal data of the owner, and this is something we have to deal with and to not get sued. Yeah. So We want to thank all those people on the big list here. Those people provided the icons we used within the presentation. So thanks to them. And big thanks to you and the organizers for everything and your attention. And we are ready for questions. Thank you.
Thank you, guys. Another scary talk.
Thank you.
So there are questions. So if you mind, take a seat. Here's someone that wants to know more about the ODB2 to Ethernet cable that you have.
Yeah.
Can the details be shared? Someone will want to investigate too, I guess.
It's pretty simple, and well, we don't need to share it because if you accidentally type in OBD2 and Ethernet at Google, you might find the instructions on the first 3 results.
Yeah, exactly. And you even can buy them off Amazon.
And you can buy them at Amazon, yeah.
So
pretty cheap. We heard that today a lot, Chinese equipment that you can use. But actually, it's just a cable, the connector, and you need 1 resistor. So
no magic behind that.
It's no magic behind it, no.
Right. And you're the ones that are selling on Amazon, right?
No.
Okay. In the future.
Right. So, so what's your threat model? An attack from the outside or a rogue ECU?
Well, it depends on. So the thing with the threat models for vehicles is that even within our company or different OEMs on different states, it's kind of hard to define the actual threat currently. So now all the car hacking stuff you see is basically it's all based on security research, academic research, for example, like we do. If the connectivity within cars is getting more and more and more, we will have different adversaries looking at possible attacks and possible business models they can disrupt, for example. But at this point in time, I wouldn't say that we have a really sophisticated threat actor or threat model.
Yeah, well, I think the question is going a different way. We looked at this from the perspective of an IT department with network monitoring. So maybe you heard of these OBD dongles. Maybe some of you use them. You can connect them to your mobile phone, and it shows you some information about the engine, and you can do logging where you drive and stuff. And it really is about the weakness of the interface. So it doesn't matter if you connect the vehicle to the local network or you plug in this Chinese $10 device. If you can get commands into that interface and the manufacturer has vulnerabilities, you have an attack vector. So, but it really depends on how the OEM implemented the interface.
Yep.
So, and we think because we spend a lot of time in what information you can gather from vehicles, and to give you an introduction to the work we did, you can identify the vehicle, and if you're good enough, you can identify certain parts. So we think targeted attacks within a network, if the cars are connected, it's possible.
Yeah.
But we have to be fair. The car has to be switched on, so the ignition has to be on. So, but you don't need much time. So if you find a device and you're quick enough, you can do damage. So
yeah.
That's what we think it's possible.
Right. And I know of those that work with the construction equipment. They are also trying to figure out what threat model to use, actually, when they design the system and design the different ECUs and how they talk to each other. But there is one that I think is very popular in the automotive industry. I don't remember the name. It's a 4-letter threat model. So I guess the question was if you have heard of that. or something similar? No. Okay. We'll let it be. So, from a risk perspective, what would you say that this research of yours and the conclusions mean in real life?
I would say, well, it's interesting for if you have service shops, for example, they have a business model, and if you are vulnerable to certain attacks with the protocol, you can take them out of business, so they're unable to, proceed with diagnostic in the shop, and customers get angry and stuff, so they lose money. So that's one thing we think it has an impact. The other thing is, like we said, it all depends on how the manufacturer implemented security measures. And if you look up things at Google and recent publications, there are manufacturers that have weaknesses, so you can send like a command. The GPAC is a good example. Whilst driving, you send in a command to change the steering angle, and you crash. So all I can say for now is please don't hook up cheap Chinese adapters to your diagnostic port.
Right, but following that reasoning, would it be possible to, I'm guessing it would be reasonably possible to create some kind of implant like we saw before on the firewall to the ODB port? Say at service, for example, if you have someone that wants to cause ill.
You mean like a supply chain attack then?
Well, or if you just go to services. Let's say that we have a criminal organization that want to create havoc on our streets. They hire someone at the service, car service place, and who just hooks up something on the cables.
I think it's possible. Yeah. I mean, you see a lot of, at least in Germany, you see a lot of commercials that they try to sell you these dongles. They can tune your car and you get more horsepower and stuff, and it's silly. But I think a lot of people are falling for that, and they just buy these stuff. And there was also a publication about insurance dongles. They have built-in mobile broadband connection, and they talk to the insurance server. And I think it came out, and after a week, the first hack was done, so you can execute remote commands. And so it's a real thing that's happening at the moment. So even with insurance dongles, and I think everyone thinks you can trust these devices. They are hardened and checked and pen tested, but obviously they're not.
But it follows the today's trend of IoT devices. You just put them out there because you have some good business idea, and
so that's a real thing.
Okay. All right, thank you very much for your time.
Thank you.
Presentation.
Thank you.
Thank you.